and we're here to present the Texas Scale Resources Risk Management and the Okhanagan Lumber Company. Well, we will start this presentation by talking about the Texas Scale Resources Risk Scoring Critique, and then the Okhanagan Lumber Mill problem with its constraints, the objective function, and the solution. Well, Texas Scale Resources, we chose this project, the risk management project, and well, Texas Scale Resources is a company, a non-profit company that operates hospitals in North Texas, and they asked us to make a quantitative model in order to improve their own and also to measure its security risk.
Okay, so what THR asked us to do was to build a model based on the model that they had employed at the moment, and create a quantitative model in order to come up with a better way to measure their security risk. Unfortunately, the model that they currently use was very complicated. The data was kind of like all over the place. We couldn't find consistency between the inputs and the outputs. So for that reason, we had to instead of creating the model, we chose to critique the model. And as an alternative, Dr. Barr presented us with another project, which is the Okhanagan Lumber Company project. And as for the critique for the THR project, we came up with several different points as how to critique their current model to determine risk. First of all, how they actually determine the different types of measurements to determine the risk score. They use a survey method in which they ask, we found that it's quite inaccurate to ask, they only ask one person in the survey, and that way they ask them a bunch of different questions, and that's how they identify the likelihood of it happening, the criticality, the effect on processes, the effect on patients. And we found this to be very inaccurate, just using one person to answer all these questions. Also, another problem we stumbled upon was the equations were not very well defined. They kind of use the same they use the same variables for different equations, and sometimes their inputs didn't match the outputs when we plugged in all the different scores. So that was one of the main problems with their method.
Yeah. So the rest of the issues that we found, besides it's pretty much a complete mess, the equations were, but they were using numerical assignments for the different problems they had. So let's say the sensitivity of information, they had 3 different levels, with being confidential patient information all the way down to public information. And normally in this type of risk scoring, you would use a percentage of something to represent the likelihood or to represent the criticality of it. So that's a scale of 0 to 100, and they're using a scale of 0, 1, 2, or 3. And this kind of throws off, throws off the end risk score because you don't have this large of a range to cover all that. And also in the textbook, where we looked at how they do the industry standard for risk management, they take likelihood into account when dealing with the criticality of the possible security breach. And Texas Health Resources didn't do it until the very end. Once they already found the weighted impact and everything, then they multiplied the likelihood by it. So that was kind of way off from where the book had the probability.
Okhanagan problem. Okhanagan Lumber Company is a Canadian company. They own 5 sawmills and 1 plywood mill. And some time ago, a consulting group asked them in order to maximize their revenue, they had to allocate better their lumber. So they asked us to create a maximizing revenue model based in these questions. And where could the manager enhance resources in order to increase production? Could separating wood types during drying increase efficiency in the process? What questions should the questionnaire manager ask the marketing manager to help improve the results of the production plan? And should Okhanagan accept an offer of 1/10 NC species 2 a year for 0.0 cents? And the approach we used was linear production. There are many constraints in this problem, and we categorize them into 3. First one are the production constraints that include the log availability. I will explain those ones in the next slide. This lab and clipper availability and the drying machine availability. The second category is assembly constraints. They include grading, gluing, and assembly of plywood requirements. And the third one is company sales minimum and maximum. Well, we had to make a constraint for each log, considering the 4 species and the diameter range, and of course the limited availability. Now, Santiago, continue.
Okay, so the log availability of the sawmills is a pretty straightforward constraint. It's just taking into account the availability of each species of log, and there's 2 types of logs. There's peelers and there's saw logs, and then basically just take into consideration the amount available per each sawmill, and that's how we build those constraints. But this is where it gets a little bit more tricky. This is the plywood plant. I'm going to explain a little bit how the workflow works. So essentially it goes from the timber supply, it goes to a plywood mill where they debark and cut it. After the debarking and cutting, they go to the steamer. This is the process when the wood is shaped. After the steamer, it goes to the lathe and clipper station. This is where the processed logs are turned into thin sheets of veneer. Veneer is essentially just thin sheets of wood. After the lathe and clipper station, they move to the dryers. In the drying station, basically dry, give the wood that nice wood steel look. And from the dryers, they go to the grading and patching station. In this station, the wood is given a grade. It's either given a grade of B, C, D, or NC, which is non-certifiable. And they go through the grading, and if they see they can achieve possibly a higher grade, it goes through patching and back to grading. And after they receive the final grade, they move to the spreaders. The spreading station is essentially where the product is formed. It involves the gluing of the different types of layers of plywood. We're going to explain later on what the different layers are and how they are assembled. And after they're spread, the wood is pressed, they're trimmed, and then they go on to sales. Okay, so I'm going to start with explaining the important stations that we use in our model to determine how to maximize revenue. First, in the lathe and clipper station, this is where the processed logs are turned into thin sheets of veneer, which is thin sheets of wood. We have to build constraints in order to convert the original units we were given for the sawmills, which were measured in board feet. The logs were measured in board feet. We had to convert them into surface square feet, since now the wood is flat. So we had to use the net surface square feet per hour in the lathe and clipper productivity figures we were given. And we built a separate variable for this particular station, and we used these figures we were given as a coefficient, and we subtracted the initial variable in order to make the conversion. We also had to calculate the annual operating hours, and we did this in order to be able to get the labor costs, because the way we were solving this problem is we were maximizing the revenue minus the labor costs. And after the lathe and clipper, it moves to the drying station. This particular station, the wood is sorted into 2 different types of wood. It's hardwood and sapwood. Basically, what we had to do here is we had to do another different conversion. We had to convert the surface square feet. We had to convert it into drying units, which in this case are minutes. So what we had to do, we put the hardwood and sapwood together in this in our model. We kind of built the constraints. You see the first few constraints are like V1 1/10. That means veneer species 1 of 1/10 of an inch thickness. V1 1/6, that's veneer species 1 1/6 of an inch thickness. And so we built a variable for every single species, and each thickness. And what we did was we took the time it takes for each type of wood to be dried, and we multiplied times the percentage of the amount of wood that's available of that certain species. And then we divided it by the conversion constant that was given to us, which is 652. And that way we converted, using these constraints, we converted the surface square feet units into minutes in the dry units. After the drawing station, it moves to grading and patching. Here, each piece of wood is given a grade. It's just split into B, C, D, or non-certifiable. Non-certifiable is basically throw it away. And we had to define new variables for each of these based on the given percentages. Each grade has a certain percentage of veneer, which is kind of determines like the quality of the wood. So we have to build new constraints based on that. And in this case, it's a grade game from now on. The differentiation between the saw logs and the peelers, which are the two different kinds of logs where the wood comes from, it no longer matters. It's just a matter of grade, which is the percentage of veneer, is the quality of wood, in other words. And this is kind of when it reaches the spreading station, this is where the product is plywood is formed. So it has 4 different layers. This is plywood because there's 2 cores. There's essentially the face, the core of the product, the center, and the back. And you can see there's 2 different cores and the center in between, and it's all glued together to form one piece of plywood. And the spreading station, this is where the product is formed. This is we have to make another conversion here. Each layer of wood equals to 32 surface square feet, and we had to essentially build constraints to find out how many batches of glue do we need for each layer of wood.
Alright, so I'm going to go through the different product types we got now. So like he was saying, we break it up based on grade, and that determines which parts go into making the overall finished product. So you can see there's 4 different products and each has a different subtype. And you can see kind of over there, that's the data we were given, but there's, this one is the 110 of species 2, grade C. So that's the base, and then there's requirements for the core back for all the different subtypes and throughout all the different products. As you can see, the tricky one is in the bottom, product 4. There is 4 different, they have the centerpiece in that one, so there's 4 different layers in that one. So that one causes little problems. But moving on, we had to name a variable for each part of the product. So this is probably the trickiest part of the project, was just keeping all these variables in order and keeping track of what we were calling each thing. So we made basically a little subscript. So starting with product, of course. So product type 3, and then the subtype followed by the layer. And as I showed you before, each one of those has a required grade for the set variable. So we make constraints for that. The product types was difficult because we had to break it down into the different layers and then place it back together into one final product variable. So starting off, we had constraints to convert the layers into that product variable. So as you can see here, this just essentially ensures that if you're going to make a product 1A, that it has a piece of each of the veneer that it needs. Next, we needed to make sure that the constraints, that there were layers that weren't overused. So we're drawing from these previously produced different layers of veneer that Santiago was telling you about. So we have to make sure we don't use more than we have. And lastly, we have to make sure that we're combining the right layers and all the different solutions for the plywood. This one's also fairly self-explanatory, just sales minimums and maximums for the products. So we took the layers, placed it into one product variable, and then there was set minimums and maximums. And this deals with the third problem we were telling y'all about earlier with the marketing manager. And I'll go ahead and tell y'all all of our objective function here. So basically we had to maximize the revenue. You can see the net realization, these first few are all peelers and saw logs from the sawmills. And those don't have a high net realization, so that's not where the money's really at. You'll see at the bottom, most of the money's in the products, which is the pieces of plywood going into the products. Also, we have to subtract all of our glue, which is the B variable right there, and all of the labor hours that we placed from the dryer, from lathe and clippers. So coming back to those problems we talked about earlier, the lathe and clipper station was the bottleneck in the process because that's where the constraint hit the maximum amount of hours, including overtime. So if they had more resources there, more hours to put towards that, then they could probably produce a lot more of the needed veneer to make more plywood at the end. Secondly, splitting the hardwood and sapwood makes drying a lot faster. That was one of the problems posed to us. We placed it together, and then we also did a model where it was split, and it was used less labor hours when it was split. Also, so they wanted to talk with a marketing manager, and they had the minimum sales limit of product 2. So we think that when they go and discuss the sales tactics, maybe they should remove the minimum sales limit because that would allow them to produce more profitable items, mostly product 3. And the fourth question, if you remember, was should they purchase the species 2 veneer for 3 cents? And the answer was no, because they don't really use any of that in the optical state. So that concludes our presentation. Does anybody have any questions?
It's actually reminded me of ITC.
Yeah.
Oh, yeah.
Different layers.
Glued together.
How did you tell your client that, like, basically you cannot do their project?
That's the tricky part. I mean, they kind of just, we sent an email out once asking for some more clarification. I don't think we ever got an email back from Ed Flegg. And so, yeah, it was just, had to let it off very easily. And
It was challenging because it was double time. We kept asking what they're trying to achieve with this, and they couldn't have it. They said, we have a way of doing it now, can you come up with a better one? So we asked them better in terms of what is it they don't like about it. Current situation is, I don't know, let me keep figuring it out.
it was so arbitrary. I mean, the equations were jumbled. The data was in 6 different spreadsheets that made no sense.
It's basically about different vulnerabilities of software. They, software systems they have, in terms of vulnerability to outside attack or to failure or healing of patient data. And they wanted a way to put a score on each one of those and to get some measure about their overall risk level so that they could track whether they were overall doing better or not. But everything just seemed very arbitrary and didn't follow any rhyme or reason. Talked about 8 nights here and
And we thought we could use like a model, like a predictive model, but we couldn't match up the inputs from the survey questions to the output of the score, so we couldn't possibly.
couldn't check.
Yeah, because we couldn't even check their own, much alone, create something new.
That was one of the ones. This is a fairly complicated case here. It's a linear program. There's a lot to it.
Yeah, the hardest part was breaking it down into the different, I guess, subcategories and then placing it all back together in, a total objective function type of variable.
We try to fill the gaps a little bit, but the end we were, we kind of like get a stretch of it. It's like, it's gonna be miles of code. We just did it in CPEX.
This is a Harvard case study. And actually, one year somebody came in this class. He's from Oregon, and his dad ran a lumber mill and had a very similar